In the previous video, we talked about how to organize our TensorFlow code by using name scopes and variable scopes and the differences between these two types of scopes. Now let's try to implement a neural network with two hidden layers for the MNIST handwritten digit recognition problem. And we will organize our code by writing multiple Python functions and also using multiple variable scopes. And our previous implementation for solving the MNIST problem had only one softmax output layer with just 10 neurons. And the input image data, those input image data are sort of directly connected with the output layer. No hidden layers, right? And we are, by using that very simple neural network, we were actually solving the so-called logistic regression problem, and we achieved a correction or accuracy of about 92%. And a 92% of accuracy looks like it's really high, but it's not really sufficiently high, right? So if we want to improve the accuracy even further, the next step is to add some hidden layers to our neural network. Right, the network that we were using last time was this kind of network, right? So all the inputs are directly connected with the 10 output neurons, the software max output neurons, and we looked at the weight matrix, the bias vector that's associated with this kind of connection, right? Today we're going to introduce some hidden layers in middle. So the layout of this neural network with two hidden layers is more or less like that. So I didn't actually draw all the arrows. I'm using this kind of block arrow to indicate there's a sort of information flowing through in that direction. But this network is fully connected, which means that every input is connected with every output, and every output. So every neuron in this particular layer is connected with every input from the layer that's right beneath it. Right, so it's a fully connected neural network. And the bottom layer is still the input layer with 785 inputs, including the bias node. And this layer is for the input images, for the flattened handwritten images, basically flattened. And then each hidden layer has 257 nodes. So I labeled it wrong. It should go from like Z1 to Z256, right? And then plus this bias neuron, or bias, the neuron that accounts for the bias term, right? Then it's exactly 257 nodes, right? But I labeled it wrong here. It's 256. It's supposed to be 256, right? And so each hidden layer is gonna have like 256 normal neurons, and then one neuron for accounting for the bias term. The two hidden layers have identical structure. In practice, you don't really have to make all the hidden neurons with the same structure. For example, at the beginning, the hidden layer at the bottom could have more neurons than a hidden layer that's sort of closer to the top, right? Making it look like a funnel, right? So you have lots of input, and then gradually you reduce the width or the total number of neurons in each of the layers as you move to the top, right? Making it look like a funnel or inverted funnel. Right? So if we just focus on one layer, suppose we look at this particular layer, right? Let's suppose we look at this particular hidden layer. If we just focus on one hidden layer, then the total number of weights for all the connections coming into this particular layer, should be equal to what? Should be equal to the total number of neurons inside of this layer, this hidden layer, multiplying the total number of inputs coming from the layer below. And all those weights, and all these weights are organized into a matrix with the column number equal to the number of neurons in this layer, and the row number equal to the number of inputs. Right? If we look at each layer, all those layers are going to follow exactly the same kind of a pattern, right? So the weight matrix is going to have a number of columns, right? And the total number of columns is going to be exactly the same as the number of normal neurons, right? Excluding that bias neuron, right? And then the row number of that weight matrix is going to equal to exactly the inputs, the number of inputs from the layer below, right? So if we are looking at this particular layer, then the number of inputs coming from the layer below is going to be the outputs from this layer, right? And then if we look at this particular layer, then the number of inputs from the layer below is supposed to be the number of inputs, the number of image inputs, basically, right? And then the total number of biases inside of the bias vector for each layer. So suppose again, if we look at this particular hidden layer, right? Then the total number of terms or total number of elements inside of the bias vector should be exactly equal to the number of neurons inside of each layer, inside of this layer. So if you would like to verify what I just said, you can go back to look at this kind of two-layered network with just 10 output neurons and all the inputs. They are directly connected. If you look at the weight matrix here, the number of columns is exactly the same as the number of neurons, because you have just one layer here, right? The number of columns is exactly 10, right? The number of columns. And then the number of rows for the weight matrix is exactly the same as the total number of inputs. That's 784. And then the number of biases, the number of elements in the bias vector is exactly the same as the number of neurons. That's 10. Right? So the same rule apply for this kind of a hidden layered structure with more than one layers, right? Now we have like 2 hidden layers and then 1 output layer. Once we understand the structure of the weight matrix and the bias vector, and we can start to write a function to define one single layer first. And then once we have that function, we can stack together multiple layers. We can write another function to stack together multiple layers to construct the neural network, right? But before we write the code, I must mention that it is now possible to train a deep neural network with an arbitrary number of layers, hidden layers, right? Any number of hidden layers with less than like 10 lines of code. If we are using TensorFlow's high-level API, TensorFlow has a huge API, but this huge API is kind of divided into like different levels. If you are using those high-level API, the estimators, those classifiers, the DNA classifiers, then you will be able to train a neural network, deep neural network with any number of hidden layers with just less than 10 lines of code. They have made it really, really easy to put together a deep neural network or DNN, right? But if we want more fine-grained control over the architecture of the neural network, right? If we want more control about how the network is organized, right? If we want more control about where do we actually, how do we organize the neurons in each of the layers, then we will still prefer to use TensorFlow's lower level APIs. And after we finish writing this code for solving this kind of 2 hidden layer problem, you will find that it's really not that difficult to actually construct a deep neural network by using those lower level APIs, and you will be able to find that it gives you more flexibility, right? Allows you, gives you more control. So we will first let's start to work on the code inside the Spider. Right. Let's open a new file. Let's open a new file, and let's just save it as. Let me put it on the desktop and save it as. And then the first thing we're going to do is to import the necessary libraries and also the MNIST dataset, right? So import, and then import. This time we're going to use, we'll need to use NumPy. And again, tutorial dot MNIST dot yeah, that's it. Import data. And then we can just import the data. This part is the same as when we did the logistical regression solution. Import data dot data sets. And then one hot. This time, the only difference when importing the data is that this time we're going to use one hot equals to false. So this one hot encoding is something that so for every input image there's going to be a label, right? The label actually tells us the ground truth about what that digit in that hidden image is, right? So if the handwritten image is a 0, then the label should be 0. If the handwritten image is a digit of 9, then the label should be 9, right? And then this one hot encoding is going to convert that label, that one digit label, into a vector with 10 digits, with 10 numbers, right? And that one hot encoding is going to put a 1 at the index that corresponds to the label, and then every other indexes will have a value of exactly 0. So that's one hot encoding, and here we're going to turn off one hot encoding when we import the data. So we're not going to ask this read datasets function to automatically convert those labels into one hot encoding. And later on, when we define the loss function, you will see why we turn off the one hot encoding. And then we can just define some hybrid parameters. So learning rate, we're still going to put it at 0.01. And then training epochs, let's put it like 40, right? It's not too long. And then batch size. This time let's give a, last time we were using 100, right? This time let's give like 50. Right? And now we are ready to write our first function. And let's just name this first function layer. Let's just define the layer function. So this layer function is going to allow us to construct everything that's related to one hidden layer or one output layer, right? So it's going to take some inputs. The first input is going to be the input to that particular layer. So if it's the first hidden layer, then this X should be the input images, right? The flattened input images, basically, the 784 element input images, right? And in practice, it's actually not a vector, right? It's actually a matrix because you are actually putting together a mini batch with 50 training examples in one run. So this X should be like have like 50 rows and then 784 columns, that kind of thing, right? And then if it's the second, if X is actually the input to the second hidden layer, then X should have like 257 elements, right? And then or 256 or 257, depending upon if you include the bias node or not. If you let's separate the bias node, right? So the input for x is going to be 256 columns, and then still 50 rows, right? Because you have like 50 examples. And then we have a second input that's n neuron, n underscore neurons. That's going to be the total number of neurons in this particular layer that we're constructing. And then we're going to need a third input that's called activation. And it's got a default value of none. Right? So what exactly is this activation input? Right? What exactly? The purpose of this particular activation input is to allow the user of this particular function to specify the nonlinear function inside of each neuron that will be used to convert the logits to the neuron output. Right? So, and this nonlinear function should be kind of configurable based upon this particular deep neural network you are trying to construct. Right? And in the past examples, we have always been using the sigmoid function as a nonlinear function to convert the logits to the neuron output inside of each neuron, basically. Right? And in this particular example, we're going to switch to a different nonlinear function, which is called the ReLU function. Right? And the ReLU actually stands for rectified linear unit, or in short, it's just a rectifier. And this rectifier, what this ReLU function is going to look like, it's going to look like that kind of thing. So the horizontal axis is going to be the logits, that's going to be the input, and then the output is going to be the neuron output, the vertical axis. The vertical axis is the neuron output. So when the logit is larger than or equal to 0, right? In this kind of a situation, if x is logit, in the previous plots we were using z as the logit, right? But here x represents the logit. So if the logit is larger than or equal to 0, then the output, the neuron output, is going to be equal to the logit. So here you see a linear function with an angle of 45 degrees. That's because the output is identical to the logit in this particular section. Right? But if the logit is less than 0, then the neuron output will be fixed at a constant value of 0. Right? So if you look at the entire function as a whole, not just as this particular section, then it is a nonlinear function because it's got a band here. If it's a linear function, then it should go all the way, right? But now it's for every logit that's smaller than 0, the output, neural output, is going to be fixed at 0. So later on, when we sort of use this layer function, when we use this particular layer function that we're writing now to construct the network, we will pass in a TensorFlow ReLU function as the activation function. Right? So if the x is actually the input to this particular layer, then its row number should be equal to the number of training examples in this mini batch. In our case, it should be 50, right? And then the column number should be equal to the number of inputs for each training example. So we can actually get the number of inputs from the second dimension of this input matrix X, right? And TensorFlow actually gives us a method for us to actually get the shape of a tensor. So let's call it n inputs is going to equal to, let's convert it into int, and then x dot, the method is called getShape. Right? If we call the getShape on this particular tensor, then it's going to give us a two-dimensional, it's going to give us an array. And the elements of this array is going to give us the size on each dimension of this particular tensor. And what do we want? Because x is going to be a second order tensor, right? So the number of rows is the size of the first dimension. That's the 0th dimension. And then the number of columns is going to be the size of the second dimension. The second dimension actually has an index of 1 because it's zero-based indexing. So the number of inputs is coming from the column number of the X matrix. In the machine learning literature, the inputs for each training example are also known as features. So now we are actually organizing every handwritten image into like a 784 pixels, right? Flattened pixels, basically. So this 784 pixels, or the grayscale on each of the pixels, is just our feature, right? So we got like 784 features for each of the input image, right? And so in the machine learning literature, it's called features, right? It's not exactly using inputs as its terminology, but this features is going to be this features terminology is only applicable to the bottom layer when you actually try to consider just the direct inputs, right, as the raw input data. But if you consider a hidden layer that's kind of in the middle, then the input for that hidden layer is actually the output from the hidden layer below it. So if that's the case, you can still use we can still say it's just the input to that particular hidden layer. It's not a big deal. So, and then for the ReLU activation function, because later on we're going to pass in a ReLU activation function in, right? If we are using the ReLU activation function, there is a study published in 2015, just 2 years ago, by He and al. Right? And in that paper, they demonstrated that the standard deviation of the weights inside of the network should be 2 divided by the square root of the number of features. So the standard deviation, that's called STD DEV, should be equal to 2 divided by, let's use the NumPy's square root function, sqrt, n inputs, right? And we will use this particular standard deviation. To create a normally distributed random numbers. And we are going to use those random numbers to initialize all the weights. So one of the difficulties when dealing with deep neural networks is the proper choice of the starting values, of the initialization values for all the weights, right? And this 2015 study has shown that if you are using ReLU function as the activation function, then the initialization value for all the weights should have this kind of standard deviation, right? And then once we have the standard deviation, then so if we use this kind of standard deviation, then the training process is going to be faster. It's going to be more efficient, right? So once we have this standard deviation, then we can use this standard deviation to create normally distributed random numbers to initialize all the weights. So let's define a new node that's truncated normal, and then it's gonna take the dimension as a tuple. It's gonna be n inputs. That's the number of rows for the initialization values. And then the column number should be n neurons, right? That's sort of supposed to be the dimension of the weight matrix, right? So the row number should be the number of inputs, and then the column number should be the number of neurons, right? If you don't believe me, you can always check this 2-layer setup, right? The weights has exactly 10 columns, and then it's got 784 rows. Right, so basically for every layer we're gonna sort of specify the weight matrix in using this particular dimension. So the column number is gonna be equal to the number of neurons inside of that layer, and then the number of rows are gonna be equal to the number of features or the number of inputs that's coming in, right? And then it also takes a second input, which is the standard deviation. Right, it's a keyword argument. So we're basically using this stddev as the input to this particular keyword argument. Here we are using the TensorFlow's truncated normal function. Right, so for random numbers that are more than 2 standard deviations away from the mean. So if the amplitude of the if the absolute value of that random number is larger than 2 standard deviations away from the mean, then those random numbers are going to be dropped and then repicked. Right, so that's called truncated normal. And now we can create a TensorFlow variable to store the weight matrix now. So W is going to equal to tf.getVariable. So we're going to use the get variable. So here we're going to use, so for the mandatory name, we're going to give it the name kernel. Initializer going to equal to init, the init that we just defined here, right? So usually the weight matrix is called the kernel inside of the machine learning literature. So when you read the machine learning papers or machine learning books, when they talk about kernel, it usually means it's the weight matrix, right? And when this variable is going to be, when this W variable, this kernel is going to be initialized, it will use this truncated normal, use this init, this truncated normal as, and with the standard deviation given here, to initialize those weights, the values of those weights. And then we can also define the bias, right? Also as a tf dot get variable bias, right? And then initializer. For the bias, we're just going to initialize to all zeros. So we're going to call tf zeros, and then we're going to give it the dimension. So the number of elements inside of this bias vector is supposed to be n neurons, right? Again, if you don't believe me, you can check this particular one layer example, right? It's the bias term, that's this particular vector. That's exactly the same. The number of elements is exactly the same as the number of output neurons, with 10 output neurons. Goes from like W00 to W09, right? So that's sort of the dimension of the bias vector, and we are using the zeros initializer. So if we are actually giving it a initializer with a fixed shape, both for this case and also for this case, the init also has a fixed shape, right? N inputs and N neurons. That's a tuple specifying the shape for the. So if we are actually using initializers with fixed shape, we are not supposed to actually give the get variable function a shape input, right? Because the get variable function will automatically use the shape of the initializer to determine the shape of the variables. So if we give it a different shape, then there will be a conflict. So if our initializer already has a fixed shape, then we are not supposed to give the get variable function another shape input. And now once we have the weights and the bias, we can compute the logits, right? So Z is just the logits is just going to be the matrix multiply X and W, right? That's the input and the weight, and then plus B, right? So if X has multiple examples inside of this X matrix, so multiple rows inside of the input matrix, then this summation is going to be done in a distributed way, right? The result is going to be as if this B row vector has been duplicated for every row of X, right? It's going to look like that without actually duplicating the B vector. So this summation is kind of a special thing that's handled by TensorFlow. And if the activation input is different from none, which means that the user has passed in an activation function, we must convert the logits to the neuron outputs, right, using the activation function. So we must convert the z's to the y's, right? So if activation is not none, so user has passed in a activation function for us, right? Then we must use that activation function to convert the logits. So we're going to return activation. Z. And then else means what? Else means the activation is still none, right? So if the activation input is none, we can just return the logits as the output of the layer function. And now we're done with the layer function. So we have finished defining the layer. So every layer is going to be constructed by using this particular function. Now the next function we need to write is the function for defining the entire network. And we will call this function inference. We'll call it inference. Right? But if you want to sort of choose a different name, for example, DNN for deep neural network, or for other kind of names, it doesn't really matter. The reason that we picked the inference as the function is because it allows you to actually compute the model predicted output from the input images. Right? It carries the forward calculation through, right? The entire forward calculation through, right? So let's use the inferences, and then X is going to be the input. In our case, it's going to be the input images with 784 columns, and then we're going to need n hidden. That's going to be used to determine the number of neurons of each hidden layer. Right. So here X is going to be the flattened images from the MNIST dataset, and then n hidden, n underscore hidden is the number of neurons in each hidden layer. Right? Of course, you don't have to use the same number of hidden layers for each, same number of neurons in each of the hidden layer, right? So if that's the case, you probably have to sort of pass in a list or something with every element of that list indicating the number of neurons for each of the hidden layer, that kind of thing, right? But in this very simple example, we're just going to use the same number of neurons for the two hidden layers we're going to construct. And now we can sort of write the body of this particular function to construct the network. The first thing we're going to do is to define a variable scope. Let's call it hidden 1. Right. And we're going to use this particular variable scope to store, to encapsulate the weight matrix and the bias vector for the first hidden layer. Right. Once we have this variable scope, we can just call the function, call the layer function. Hidden 1 is going to equal to layer 1, layer, and then X is going to be the input, and then n hidden is the number of neurons for that first hidden layer, and then our activation function. Activation is going to equal to what? It's going to equal to tf.nn.relu. That's the TensorFlow's ReLU function, right? NN means neural network, and then ReLU function is one function inside of that neuron, that NN. So if you actually have defined this particular variable scope, that's called a hidden 1. Then these two, the kernel matrix, the kernel, right, and then the bias matrix, their names are going to be prefixed with hidden 1 and a slash, right? So for the weight of for the kernel matrix and the bias for the first hidden layer, they are going to be inside of the hidden 1 namespace, variable space, variable scope. All right. So that's our first hidden layer. That's our first hidden layer, right? And now we can create our second hidden layer in the same way, right? And store all the variables under a new variable scope that's called a hidden 2, right? Let's create another variable scope, tf dot variable scope. Let's call it hidden 2. So hidden 2 again we call the layer function. But now what's going to be the input to the second hidden layer, right? The input to the second hidden layer is supposed to be the output from the first hidden layer, right? So it's a hidden 1 that just returned from the first code layer, right? And then we're still gonna use n neurons as the number of neurons for the second hidden layer, right? And then the activation function is still gonna be ReLU, right? That's gonna be our second hidden layer. And the last variable space, variable scope we're gonna create is called the output. So with tf dot variable scope output, that's the 10 softmax neurons in the output layer, right? But this time we're not gonna sort of use any kind of activation functions. We're just gonna output the logits layer, and then the input to this particular output layer is supposed to be hidden 2. And then the total number of neurons for the output layer is 10, right? Because we have like 10 digits from 0 to 9. That's 10 output neurons. And then for the activation function, we are not going to supply anything. So if we are not supplying any activation function, the activation function is set to none, right? And if the activation function is set to none, then it's going to return the logits directly without applying the nonlinear function, right? So here the output is assigned to the variable logits, right? That's exactly logits basically. And neurons, undefined variable, and hidden. Sorry, it's not and neurons and hidden. Right. And then we can just return the logits. Right, and the other functions are going to use this return the logits to compute, for example, the cost or the loss, and we will leave other functions and the rest of the code for the next video.